Hello and welcome. Today we'll be talking about transformations of graphs. So these are the problems where you're given some kind of equation for a graph, f of x equals 3x squared plus 5. And you're asked, what the heck happened to it? Maybe they say, tell me what transformations have happened, and you have to use words and symbols, or they'll just say to graph it. Now, in order to deal with a problem like this, we have to understand how these coefficients or constants, it's this coefficient here, it's this constant here, would affect the original base graph. So let's go through the general strategy before we see some specific examples. The general strategy is, number one, you need to identify your base function or base graph. So it could be x squared, it could be log of x, it could be e to the x, and so on. There are many possible base functions. For most of this video, we're going to focus on x squared. It's the most common one to mess with, and it's a pretty straightforward and intuitive graph to deal with. So let's see what that looks like. So over here, we have f of x equals x squared. And what this looks like is a parabola with the vertex at the origin, 0, 0. And it's just going to cup upwards like so, up and over, forever and ever. Okay, standard parabola. Then, once we've identified what the base function looks like, and we have an intuitive understanding of how to graph it, we would follow it up by identifying what changes are made. And this is the hard part. But really, there's only two steps. See what base function you're working with, and see what change between it. Let's talk about how we identify what changes are made. So, in order to identify some changes in a function or a graph, there's going to be a few key things to keep in mind. Number one, inside of any parentheses will be opposite of what you expect. So whatever's happening to the inside will do the opposite of what you expect. It's also going to do a left/right action on the graph. So it's going to move it left/right, it's going to squeeze it left/right, it's going to flip it left/right, things like that. The second thing to keep in mind is that the outside, whatever happens on the outside of parentheses, is what you expect. It's expected. And then it's going to move it up and down. It's going to be vertical action. So inside of parentheses is going to be left, right, or horizontal action. Outside of parentheses is going to be an up, down, or vertical action. And lastly, negatives flip, right? So if you have a negative multiplied by a function, it's going to flip it. Let's see what that looks like. If we have, for example, this function here, f of x equaling x plus 2 squared plus 3. When you look at this, you can identify, oh, there's a square, so it's going to be like the original base x squared function. So we know what it looks like generally. Now we have to know, what the heck does this 2 do? Well, this 2 is on the inside of the parentheses, so it's going to do the opposite of what I expect. When I see plus, I think it should move up or to the right, but I'm going to do the opposite. Furthermore, because it's on the inside, it's going to be a left or right action or a horizontal action, which means that this is going to be moving the graph left by 2. This would be a shift left by 2. So once again, it's positive, but because it's inside the parentheses, I'm going to do the opposite and move it left instead of right. Now when we look at this 3 over here, it's on the outside of the graph, so it's going to do what we expect. And it's going to be an up-down action, a vertical action. And so this is going to go a shift up by 3. And it's really easy to read this graph. Let's see what that looks like. Here we have the base function, f of x equaling x squared, just a normal parabola centered at the origin. And I'm going to think, how am I going to move it left 2 and up 3? Well, I'm going to focus on this vertex here at the center. So I'm going to think of that dot as my focus. I'm going to move it left 2, so 1, 2, negative 2. And I'm going to move it up 3, 1, 2, 3. I'm going to draw that dot right there. And then I can draw the parabola just as normal. So it's going to look something like this. A normal parabola just moved left and upwards. And that's how you would transform this original graph. And again, all I did was identify what the base graph was, and then look at what kind of transformations are happening to it based off of this system. Inside being opposite, left, right. Outside being expected, up, down, and negatives flipping the graph. Let's see some more examples. All right, let's try this one out. So we have f of x equals 2 times x minus 1 squared plus 4. This is once again an x squared base, and so I can imagine my original parabola going right here. And I have to identify what the heck's happening to it. Well, there's a few things happening to it. First, I see, oh, well, there's a negative on the inside. That's a left-right action. This is going to move it to the right 1 because inside is opposite. There's a plus 4 on the outside. That's going to do what I expect because it's on the outside. That's going to move it up, down. So I'm going to say up 4 from the outside. And lastly, there's something new here. This 2. This is not adding and subtracting. This is multiplying. So adding, subtracting moves it left, right, and up, down. Multiplying is going to be a stretch or a shrink. What is dilation? So either stretching or shrinking the graph. And in this case, because it's on the outside, it's going to do what I expect. It's going to stretch the graph. But is it going to stretch it upwards or left, right? Well, once again, outside is what you expect, and it is a vertical component, up, down. So I'm going to stretch vertically on my graph. So what's that going to look like? Well, I'm going to go over here. I'm going to plot my vertex, my key, point of interest. It's going to, instead of being at the origin, I'm going to move it right 1. So put a 1 right here. I'm going to move it up 4. I'll put a 4 up here. I can draw my dot. It's going to face upward like usual, but instead of drawing it normal like this, kind of thick and wide, I'm going to write tall and skinny because it's being stretched vertically. So it's going to go up like that, a little skinnier than usual, a little taller than usual. And that would be my graph. Pretty easy, just looking at what changed and knowing what my original looks like. Let's try another. All right, let's try this one out. So in this case, we have a negative 1/2 times x plus 2 squared minus 3. Once again, it's an x squared equation. And so we're going to think of our base parabola as our original picture. The only big difference here is that this negative over here on the outside is changing the setup. So we're going to see what that does. This negative is going to flip our graph. It's going to perform a flip. But there are 2 ways to flip. You can flip over the x-axis or you can flip over the y-axis. So how do we know which? Well, once again, it's on the outside. So it's going to do what we expect. And it's going to be a vertical action outside of vertical actions. So vertical actions in this case would look like flipping over the x-axis to this point here. And so I'm going to say flip vertically over the x-axis. We'll see what that looks like when we graph it. Furthermore, we have a 1/2. That's going to be a shrink by 1/2. It's on the outside, so it does what we expect. That's why 1/2 shrinks it instead of expanding it. And it's going to shrink it vertically, up, down, also because it's on the outside. Over here, this 2 is going to be on the inside, doing the opposite. So it's going to be a left shift by 2. And on the outside again, we have a negative 3, so it's going to be a downshift by 3. Let's see what that looks like. So over here, we're going to graph our function, and we're going to have a vertex, our origin, is going to be based not at 0, 0. It's going to be left 2, so I'll put a negative 2 right here, and down 3. Put a negative 3 right here. And I draw my dot. That stretching and shrinking and the flipping won't really affect this dot, this vertex. It's not going to move where the vertex is. So let's see what happens. I would normally draw my parabola going upwards and kind of thick, but because of that 1/2, I would shrink it vertically so it'd be kind of wider like that, a little bit wider. I'm exaggerating for effect here. But there's something else happening, that negative. So not only do I have to draw it wider, I have to flip it upside down. So I'm going to draw it like this, wide and upside down. That would be what our graph looks like. So there are 4 effects happening. It's being flipped vertically. It's being shrunk by 1/2 vertically. It's being shifted left by 2, shifted down by 3. And as long as you follow the system of, oh, inside opposite, outside what you expect, inside left right, outside up down, these can be made much more manageable. So we spoke many times about how to transform the x squared graph, but it applies to all other base graphs as well in the same manner. So some common graphs that you will have to transform, move around, flip, and so on are going to be as follows. This y equals x squared, which is just a vertex. For this, you're going to focus on that vertex point to show you where it's going to start. Then there's y equals x cubed. This is similar to the x squared graph. In this case, it's going to go up and to the right, and then down and to the left. So it's kind of a squiggly sign. It's kind of like a parabola, but the right half is upwards and the right half is downwards. They're both little halves of parabolas, if you can think of that. For y equals 1 over x, this is kind of interesting. It's going to look like this. If I have an x and y axis, it's going to have a line coming from the top down towards the right. So it's going to look like so, where it's kind of hugging the top right of the graph. And similarly, on the bottom side, if you have negatives, it's going to hug all along and kind of curve outward based off of this. For the y equals square root of x graph, that's actually a parabola just on its side. And notice there is no negatives. You can't have a negative inside the square root. So it's going to look something like this. If I have a little graph, it starts at the origin and it goes off and to the right. So it's like a parabola on its side with no bottom part. Y equals e to the x is interesting. It's going to always hit at the number 1 for its base function. So you can think of the number 1 right here. It's going to have a dot there. I think of that as its kind of vertex. So whenever you move e to the x up, down, left, or right, you're going to move that starting point up, down, left, or right. And then the way the graph works is it's super small, and then it gets up, and then it kind of explodes upwards. That's the exponential graph. The log graph is very similar, but it's just the opposite. So, because logs are just inverses of exponents. So instead of a 1 on the y-axis, I'm going to have a 1 on the x-axis. I draw my dot there, and it's going to very tightly hug this graph as it goes exponentially. It's going to cut through here, and then it's going to go off to the right. And once again, for this, I would recommend focusing on this little vertex here. In fact, for any of these, you should be able to identify one spot that when you're moving left, right, up, and down, you can say, I'm moving that thing there. So for the parabolas, it was the vertex. I'm going to move that up and down, left and right. For the x cubes, it would be the origin, this little middle piece of it, moving that up, down, left, and right. For the square root of x, it would be the origin here. For e to the x, it'd be where it crosses at 1. So if it moved up by 2, it would instead cross at 3, and you draw a graph right there. Similar for log of x, it's where it crosses at 1. So if this whole thing moved up by 2, it'd be a little harder to draw. But if it moves right by 3, then it's going to go over here to the 4 point, and you can see that that's going to be where your vertex is. Lastly, this y equals 1 over x is a little more annoying because I don't have a nice, easy point to pick. What I would say is, either focus on this origin, there's no point there, but focus on it as your center and draw around it, or even just think of the whole axis moving around. So if I were to move left and up, I would think of, oh, well, suddenly my axes would be something like right here, and they would meet over here, and I can draw my graph like this, where it's the same graph moved up and to the left. And then if I wanted to, I would even erase out this little axes because my teacher doesn't really want to see that in my answer. And suddenly I have a nice graph of a 1 over x moved left and upwards. So as a brief recap, how do we deal with these? Number 1, identify your base function, right? X squared, e to the x, and so on. If you can't identify the base function, you're not going to know what it looks like. So focus on memorizing all those base functions. Number 2, identify the transformations happening to it. Number 2, we're going to identify the transformations happening to our graph. Is it being moved up? Is it moving left, flipped, stretched, and so on? When identifying those transformations, there's a couple of key rules to remember. You want to remember that inside is opposite and it's a left-right action. It's going to be a horizontal action. And the outside is what you expect to happen, and it's going to be an up-down action. Furthermore, any negatives are going to flip the graph. And with that, you can solve any transformation of graphs problem and make it much simpler for yourself.